Okay, so last time we talked about higher order differentiability. So remember, this was the definition that a mapping from an open subset O of a locally convex space U into a locally convex space V is of class CK if it's first of all of class C1 and its derivative is of class CK minus 1. So that was our definition of what it meant to be class CK. And so this is a kind of bootstrapping definition. So we already know what it means for something to be of class C1. And so what this definition says is that it's class C2 if it's class C1, and its first derivative, d phi, is of class C1. And then similarly, you go on to class C3, means that d phi is of class C2. And so the definition bootstraps like this. And so I didn't say last time, and I'll say here, that phi is of class C infinity, of course, if it is of class CK for every K. Okay. So let's look at an example. Okay, so last time we had an example of just a linear mapping, phi, from U to V. Okay, so okay, so a continuous linear mapping, and so we saw last time that phi, a continuous linear mapping, is of class C1, so it's once continuously differentiable, and d phi, and so remember the differential is defined as a mapping from the open subset O cross U into V. Okay, so it's going to take two arguments, both of them from U in this case, because the open subset O is all of U. So it takes two arguments, X and U, and it simply gives you back phi of U. Okay. So now we want to, so we claim that phi is in fact of class C infinity. So continuous linear mappings are infinitely differentiable. So it's of class C infinity. And so certainly, so to verify that it's of class C infinity, you need to show that it's of class CK for every K. Okay, so that's what we'll do, and we'll do that by induction. So certainly, of course, phi is of class C1, as we showed last time. Okay, so now, by induction, suppose that phi is of class C, let's say M, for some M. And, well, let me say M is greater than 1. Okay, so then what I want to show by induction is that it's of class Cm plus 1. Okay, so then B is of class C1. So if I want to show that it's of class Cm plus 1, I have to do two things. I have to show that phi is of class C1. That's clear. Okay, so phi is of class C1. And then I need to show that its derivative, its differential d phi, is of class. Uh, so to show n plus 1, I have to show that its derivative is of class Cm. Okay, so moreover, so also d phi. Okay, so d phi here is a map from u cross u to v. Okay. And what does it do? Well, it sends x and u to, well, phi of u, as we saw above, and as we saw last time. All right. So what I need to show is I need to show that this thing is of class Cm, and if I show that if I show that it's of class Cm, then it follows that phi is of class Cm plus 1. Okay, so we write d phi, okay, um, equals phi composed with the projection onto the first factor. Okay, so PR1 is a mapping from U cross U into U, which sends U1, U2 to 1. Okay. All right. And I'm sorry, that's U. That's PR2, not PR1. Okay, and so this is clearly true because it takes the two arguments and returns phi applied to the second argument. Okay, so that's certainly true. Okay, so note that phi composed with PR2 is continuous linear. Okay, so what is this a mapping to and from? This is a mapping from U cross U into V is a continuous linear mapping. Okay, all right, just because phi is a continuous linear mapping. Okay, and of course the projection is too. All right, and so therefore by the induction hypothesis, phi composed with PR2 is of class Cm, because I'm assuming, so I've said here that I'm assuming that phi is of class C1, but the induction hypothesis is really more than that. The induction hypothesis is that every continuous linear mapping is sorry, here. I've said that phi is of class Cm plus 1, but what I mean, of course, is that every continuous linear mapping is of class Cm, and this is a continuous linear mapping, and so it's of class Cm. Okay, so by the induction hypothesis, this is of class Cm. Okay, and therefore we conclude that phi is of class Cm plus 1. Okay, and so this is true for every m, and so therefore phi is of class C infinity. Okay, so linear mappings are infinitely differentiable, which is a fact that we will use. Okay. All right. So let's talk a little bit. So the advantage of this definition, and you can see this from you can see. see this in this example is that we've actually never computed any of the higher derivatives of this mapping. Okay, we've just gotten by looking at d phi, the first derivative, to conclude things about higher order differentiability. Okay, but nonetheless, you want sometimes to know what the higher derivatives are, just like we know what the first derivative is. Okay, so let's talk about what are the actual derivatives, not just differentiability. Okay. Um, all right, so so there's a bit of a notational development that has to happen here. So we'll go through that. All right, so we let U and V be locally convex spaces, and let uh, O be open, and we let phi be C K, let's say. It doesn't matter. We're going to, for large enough K that everything we say is going to make sense. Okay. All right. So then I know that d phi, so maybe let me do it like this. So phi, not that phi, capital phi. So I know that phi maps O into V, and d phi maps O into, sorry, O cross U into V. Okay, so if I keep this process going, d phi, okay, um, and so d phi has as its domain this open subset here of U cross U, okay? And so that means d phi, d of d phi is going to map O cross U cross U cross U into V, okay? Now, that actually has too much stuff. There's kind of redundant information here. And so what you'd like to do is you'd like to simplify the domain of the derivative, because when you differentiate here, you're differentiating in this component here, and somehow this component is the direction in which d phi is being differentiated, and really we're talking about differentiability in O, and so you expect that, so this derivative somehow should be relevant, but this derivative should be less relevant because this corresponds to differentiating U, differentiating in the direction that I'm differentiating with respect to. So we somehow want to pare down the number of copies of U that are involved here. Okay, so let's see how you do that. And you do that basically with notation. Okay, so let's let U1 in U and denote I U1 d phi. Okay, so this now is going to be a mapping from O into V. Okay, so U1 here is fixed with respect to this mapping to this mapping I U1 d phi. Okay. And all I do is, so it takes a point X and it maps it to, of course, D, V, X in the direction U1. Okay. And so this mapping, sort of isolates the X dependence that I care about. Okay. All right, so now I can differentiate this thing in the usual way. Okay, so I can go d of this. Okay, and right? Because this is now just a mapping from O into V, like phi was initially. Okay, so this is going to now be a mapping from O cross U into V again. Okay, it's just this mapping kind of carries U1 along as a parameter. All right, so then I can keep going. I can now, again, I have this extra u here that I don't want to continually differentiate with respect to, and I get rid of that by choosing a u2 and sticking that in as a parameter. Okay, so now for u2 in u, okay, we have, all right, so the notation now gets a little cumbersome, but nonetheless it's straightforward. Okay, and this again will be a mapping from O into V. Okay, and if you think about what we're going to do here, and so this is going to be it's going to send a point X to D of sorry, I need more space here. Oops. All right. Um, okay, so it's going to be like this. Okay, so this mapping now, again, is a mapping from O into V. And when I calculate this thing, this is the definition of what this symbol means. It means that I differentiate this mapping, which is a mapping on O, okay, and I differentiate X in the direction of U2, okay. Right, and so I can continue to do this up to presumably this needs to be proved, but presumably you can continue doing this k times. Okay, so I'm going to state a result, which tells you that you can do this up to k times, but for now let's just write the notation down. Okay, um, so then you have I U K. Okay, then it's D, I, and maybe I'll do it like this. I, U, K minus 1. All right, and then you just keep going down to I, U, 2, D of I, U, 1, D, V. Okay, so none of this makes sense a priori, but by this device, we make this thing here depends on the right number of u's and x's. Okay, so it's first of all it's a function of x. Okay, so just like all the other cases, this is a mapping from O into V. Okay. All right. And it only carries k of these parameters, directions in which I'm differentiating. Okay. Whereas up here, for the second derivative, I would expect to have two directions in which I need to differentiate, but oops. Okay. But if you just do d of d, you get three. Right? And it gets worse and worse as you differentiate more and more times. Okay. All right. So with this notation, we make a definition, and then we state a result. Okay. Um, so all right. right. So the so we have U V LCSs, O open, and V going from O to V. Okay. And we denote, okay, D parentheses K phi. Okay, so this one is going to be a mapping from O cross K copies of U, okay, corresponding, as we'll see, to the KUs here, okay, into V. Okay, and so what does this do? So this sends X U1 up to UK into um, this thing. So I'm going to copy that. Of X, right? Okay, and so at this point, I don't know if any of this makes sense, and so I'll just write when this is defined. Okay, so this is the kth iterated partial derivative. No, not partial derivative, sorry. The kth iterated derivative of phi, okay, in the directions u1 up to uk. Okay, so that's, we call these the iterated derivatives. Okay, as opposed to uh, say this, okay, which is D applied to D, and then you could go D applied to D applied to D, and keep going that way. So that's another iterative procedure, and as we'll see in the next result, it kind of contains the same information, but this has no redundancy in its definition. Okay, so let me state the result here. So what you would like to be true then is what you'd like to be true is that phi, this phi is of class CK precisely when this thing exists, right? So when all of these constructions make sense, and then this mapping is continuous. Okay, so that is what is in fact true. Okay, so I'll state that as a proposition. Okay. Um, all right, so the with the same notation as in the definition, we have two equivalent statements. The following equivalent. So the first statement is that phi is class CK, and then the second statement is that, and so maybe I'll do it like this because I want to just sort of personal preference. I'm going to allow K to vary here. And I'm going to say that, so this is of class CM, where M, of course, is a positive integer. And so being of class CM is equivalent to the iterated derivatives d k p exist. Okay, so exist means that this makes sense. Okay. And our continuous for k less than or equal to m. Okay. All right, so I'm going to prove just one direction of this, which is the easy direction. The hard direction is actually hard, and there's a proof of it in the course text, but it's a challenging proof. Okay, so we'll do the easy direction. Okay, so we'll prove that one implies two. Okay, so this seems, certainly it seems like if this is true, then it seems like you should be able to, construct k of these derivatives for any k up to m. Right? So let's just prove that you can do that, and of course we're gonna do that by induction on m. Okay, so for m equals 1, of course it's true because d1 phi is d phi. Okay. All right, so we saw that with our definition here. All right, so this thing is just d phi. All right. And so now let's suppose, suppose um, that the result is true for m equals r. Okay, so that means that phi being of class CR is equivalent to the iterated derivatives up to order R exist and are continuous. All right, so that's the hypothesis. Okay, so we're going to suppose that the result is true for m equals R, and take phi to be of class CR plus 1. Okay, so then I need to show that these iterated derivatives exist for k less than or equal to r plus 1. All right. Okay. So, first of all, by the induction hypothesis, since d phi is of class CR, okay, I know, so the iterated, iterated derivatives of d phi exist up to order R. So dk d phi exist and are continuous for k less than or equal to R. Yes, that's the induction hypothesis. All right. So now let's let k be less than or equal to r plus 1. Okay, and then I'm going to show that the iterated derivative up to order of order k makes sense. Okay. All right, so I need to differentiate in k different directions. Okay, so let's let um, u1 up to uk be in u. Okay. And I need to show that this mess that I'm about to write down makes sense. So I, U, K of D of I, U, K minus 1, dot, 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 D of I, U, 1, D phi, okay, of X. All right, so that's the thing I need to show makes sense. All right. Okay, so now I'm going to use the fact that the iterated derivatives of the derivative exist up to order k, right? So I'm going to take the first term here, and I'm going to rewrite that as d phi applied to x and u1. Okay, so this is equal to I u k. All right. And so now I'm thinking of d phi as being a function of two variables. And so my in this formula here, if I'm replacing phi with d phi, which is what I'm doing, okay, then I can't just use u's because the domain here is O cross U. I have to use something in U cross U. I have to replace these with things in U cross U. So I'll write down the formula, then I'll explain why it's true. Okay, so this is UK 0, okay, then D of I UK minus 1, 0, and then D I UK, yeah, sorry, that's U2, 0, okay. Um, and then it's D phi, okay, and now it's evaluated, let's see, I think I need 3 closures here. Now it's evaluated at X, U1. Okay, so the easiest way to understand this formula is to go not from here to here, but to go from here to here. Okay. Because what I'm doing in this formula is I have this function d phi, okay, of two variables, x and u1. Okay, and so what I'm doing is I'm doing the exact construction that I did up here. Okay, so these I used, I'm doing exactly that construction, but not to phi, but to d phi. And so when I do my differentiation, it's not just going to be a u2, there has to be a u2, and then there has to be another vector corresponding to the fact that it's a function of the two variables, x and u1. Okay, but I'm going to choose the second one to be 0 in every case. Okay, right? So in every case, I'm differentiating this function of two variables. Okay, here in the direction of u2 0, and why is it 0? Well, it's because I'm only interested in differentiating with respect to x, not with respect to u1, and so that's why I put the zeros here. Okay. All right. Okay, good. This then is equal to, okay, um, um, by the induction hypothesis, okay, I know that this thing is defined because now the order of derivative that I'm taking here is k minus 1, right? So it goes from 2 to k. So it's of order k minus 1. And so that one exists by the induction hypothesis. So it is d k minus 1 of d phi. Okay, so not There's, this d is d of phi is a function of the variable x, and this d is the derivative of this as a function of the two variables x and u. Right? So this is a complicated but not difficult proof. All right. Um, and so then I'm going to evaluate this at a point. Okay, so the point is this point. So x u1. Right? Then I need to stick in, just like in the definition here, I need to stick in the directions in which I'm differentiating, and um, those are these directions. Okay. All right, so it's u2 0 up to uk0. All right, so that's a bit of a mess. But at the end of the day, this does it for you because the induction hypothesis is that this thing makes sense, okay, and is continuous as a function of all of its arguments, okay, and so therefore this thing makes sense and is continuous as a function of all of its arguments, okay. So this shows that dk, oops, k phi is well defined and continuous. For k less than or equal to r plus 1. Okay. All right. So my suggestion would be to understand this proof because it'll make you understand what this um, it'll make you understand what this symbol really means. Okay. Um, so it's a very simple proof, but it's notationally baggy. So it's worth investing a moment or two to understand that. Okay, and then there's the other part of the proof, which I'm not going to do because it's um, okay. All right, there's certain things that are complicated, and they're complicated in a way that's not necessarily worth understanding. Right? So I'll probably hurdle over a lot of those kinds of things. All right. So this is good because what this does is that dk phi is the analog. Whoops. The analog of this dk phi, the higher order derivatives that you would have learned in your multivariable calculus course. And we'll establish the connection between those things a little bit more carefully just now. But this is intended to replace the thing that you're familiar with. There's a big difference, okay? So this thing is a map from O cross UK into V, whereas this thing, okay, is a map from O into, okay, so what kind of mapping is let's say the second derivative, okay? So the second derivative, so let me write it down in sort of vector calculus form, okay, just to make something concrete that we're all going to be familiar with. Okay. And so let's say here that phi is a mapping from Rn to Rm. Okay, so here phi, so A is going to go from 1 to m. Okay, so phi is going to have m components corresponding to the fact that the map takes its values in Rm, and then you're differentiating with respect to n independent variables. Okay, and this you would have called the Hessian, right? So if you assembled, if A was equal to one, sorry, if M was equal to one, okay, then you assembled these things into an n by n matrix, and you called that the Hessian. Okay, so when M is not equal to one, then I guess you could think of there being a bunch of Hessians. I don't know if that's necessarily a good way to think about it, but I guess you could do that. Um, but the point is, the second derivative is this d phi, in the case of k equals 2, is represented by these collection of partial derivatives, second partial derivatives. Okay. So what kind of object is that, is the point? Well, it's a matrix. You can think of it as a matrix. Um, and it's symmetric. Okay, so if phi is of class C2, okay, so twice continuously differentiable, um, then this thing doesn't depend on the order of j and k. So if you replace j with k, you get the same result. So taking partial derivatives, it doesn't matter what order you take them, provided the functions are sufficiently differentiable. Okay. And so what this means is that this isn't a linear mapping like the Jacobian, it's a multilinear mapping, which takes values in Rm, okay? And it's multilinear because it takes two vectors in Rn, corresponding to these two indices here, okay? So this is going to take its values in the set of multilinear mappings, so k. Okay, so k corresponds to something which takes k arguments. They're going to be symmetric. Okay, and it's going to take k arguments from Rn and take values in Rm. All right, that's what the derivative is. All right, so in the k equals 1 case, then this is just a linear mapping from Rn into Rm. But for higher k's, it's going to be a multilinear mapping, again corresponding to the fact that you have all of these partial derivatives. Okay. All right, so this thing, and we're going to talk more about this note. I'll carefully define this notation here in a minute, but I wanted to, but it's good to sort of see what that looks like in the case that you're familiar with, because now we're going to compare it to what's going on over here. Okay. Um, and so the point is, just as the derivative d phi isn't just the derivative, it's the derivative evaluated in a direction. Okay, the kth derivative is the derivative evaluated in k different directions. Okay, and here we leave off the directions. Okay, we just right, there's no u's in the formula for capital DK phi. All right. So that was just some making connections to things that you know about. Let's be a tiny bit precise about that. Okay. So I talked a little bit about multilinear mappings last time. Let me do that carefully now. Okay. So let U1 up to UK and V just be vector spaces, not topological vector spaces, or locally convex spaces. Okay, so a mapping phi from U1 cross UK into V is K multilinear if for all right, so basically what multilinear means is that it's linear in each argument. All right, so if I freeze all but one argument here, okay, then it's linear in the remaining argument. All right, so all I'm going to say is I'm just going to write that down precisely. Okay, so if for uj, let's say uj0, and the 0 is to emphasize that it's fixed, okay, in uj, Okay, and j is going to be from 1 up to k, and I'm going to leave off, let's say, L. Okay, so this means that I'm going to fix every argument of phi. Okay, I'm going to fix every argument except the elf one. Okay, and so these uj knots are the things that are frozen. Okay, so blah 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 blah. The mapping, which maps ul into phi with all of these frozen ones, uj0 up to ujl minus 1. And then here I'm going to have ul, and I'm going to have oh, sorry, not, I'm sorry, u10, get this right, sorry, u l minus 1, 0, okay, and then ul plus 1, 0, up to uk0, okay. All right, so again, this is just tedious, but this means I'm freezing every argument except the elf one, okay? And that mapping should be linear. That's what it means to be multilinear. Okay, so that's what a multilinear mapping is. All right, so a multilinear mapping. So let's say all of these u's are the same, which is actually going to be the case that we're interested in at the moment. So a K multilinear mapping B from U K, so K copies of U into V is symmetric if for every permutation sigma, okay, so sigma is going to be in the permutation group, okay, so this thing is the permutation group. One, okay. Okay, so for every permutation sigma, it holds that phi of, and so basically I'm going to take the arguments and permute them, okay, and it's independent of the permutation, okay, and the way you write that is sigma 1 up to u sigma k is phi of u1 up to uk, right? So no matter how you permute the order of these u's, okay, you get the same result. That's what it means to be symmetric. All right. Okay, so then you have a simple result, which says that this mapping, dk, right, if you fix x, it's multilinear and symmetric in UK. All right, so let me go back to our original setup here. So not just here, we were just talking about algebra. So now let's return to our calculus setup. Okay, so we have U and V are LCSs. O is open. Okay. Um, and I'm going to assume that phi is of class CK. Okay. So then the conclusion is going to be that for each, okay, so again, if I choose a value of x, the resulting thing is going to be k multilinear and symmetric in the U's. All right, so just write that down carefully. So then, for every x in O, okay, the mapping okay, so it's going to map UK, all right, and it's going to take k of the U's, and it's going to map it to dk phi of x u1 up to uk in V. This mapping is k multilinear and symmetric. Okay. All right. And so that's a fact again that's familiar to you from multivariable calculus. So the multilinearity sort of corresponds to the fact that you have these indices here. So I've only written this out in the case of k equals 2, okay, where you have two indices. That's your multilinear. And symmetric means it doesn't matter which order you take the partial derivatives, you get the same thing. Okay, so this is analogous to things you already know about. All right. So the proof of this is tedious. The proof of the symmetry result even in calculus, in multivariable calculus is tedious, and maybe you didn't even see that result. It's called, um, so the symmetry is sometimes referred to as Schwarz's lemma. Yeah. All right, so again, I'm not going to prove that. Like I said, the proof of this is so first of all, the proof uses the proof that you of this result that comes from multivariable calculus, and then adds a little bit of stuff on top of that. And again, that's one of those results that's kind of long and tedious, and I don't think has any useful tricks in it. Okay, so maybe we'll skip over that. Hmm. But we'll definitely make use of this fact. Okay. All right. So let's make a connection now between what we do and what you do in multivariable calculus in terms of derivatives. Okay, so what's the connection between this thing and this thing precisely? Okay, so definition. Oh, so I should have set up here. Let's have some notation that we have for, so I can do it down here. Notation. And so notice also that this mapping, is certainly continuous, okay, because if phi is of class CK, as we just saw, DK is continuous, DK phi is continuous, right? So this mapping from the U's into V is certainly continuous. Okay, so we're interested in continuous multilinear mappings, and we have notation for those, is the point. Okay, so L of um, U1 to UK, right? So commas and then a semicolon. Okay, so these ones represent the domain, and this one represents the codomain. Okay, so this is the set of K multilinear continuous mappings. All right, so that's the notation. And I'll try to remember to put an F there to emphasize the fact that we're talking about possibly real or complex things. Okay. And then L, let me see, let me make sure I use the same notation. Okay, so sim F K, okay, of U V. Okay, so these are going to be the symmetric multilinear things. And so, all of the U's have to be equal. So I just put a single thing there. And the multilinearity I represent with the K here. So these are K multilinear, symmetric, and continuous. Okay. All right, good. So that's the notation. So in other words, okay, what we have is that the mapping U U1 U K to U K phi is E L K sim. That's what Schwarz's lemma says. Okay, and this is true for every X in O. Okay. Sorry for all the tediousness, but all of this stuff is going to be used later, so we have to sort of get it all down, unfortunately. Okay, good. So notation. This mapping, the one I just wrote just above, mapping is denoted by, and so I just make reference here to the usual calculus notation, d phi from d phi of x from u k into v. All right. Okay. And so notice, let's just make explicit the relationship between big D and little d. We have d k phi of x u1 uk is d k phi of X. Okay. And now it takes as its arguments U1 up to UK. That's the relationship between these things. So important. So I said, when we talked about the derivative, I said that big D, okay, so we talked about D phi, okay, as a mapping from O into the set of linear mappings from U to V. Okay, so here we have dk phi is a mapping from O into the symmetric multilinear mappings. And what I said previously was that this thing is generally not continuous. Well, of course, that's also true here. Okay, so I'll just write all that down. Oops. Just with first order case. The mapping capital DK phi from O into LK sim, symmetric K multilinear mappings, is not generally continuous. Even if little d is. Okay, we talked about this in a little bit of detail in the last lecture. There's two problems with connecting or sort of ascertaining the continuity of dk phi. One is that this thing is not continuous. Okay. And in fact, just like the set of linear mappings between two arbitrarily locally convex spaces U and V does not have a natural topology, well, that's also certainly true of the symmetric multilinear mappings. So, even to talk about continuity of this thing, it's not clear how you even do that. Okay, so, that certainly gives cause for saying that it's not continuous. So this thing is continuous, even though this may not be. Okay. And moreover, the mapping which takes a multilinear mapping and substitutes in values, so this is like the evaluation map that we saw last time. Okay, that's also not generally continuous. Okay, and so also, as in the first order case, the mapping the evaluation mapping, right? So this one takes multilinear mappings. So let's say, let's maybe make them even symmetric, doesn't matter. Okay. Okay, so this takes a multilinear mapping and arguments, U1 up to UK, and evaluates it. That's why it's called the evaluation mapping. This one is not symmetric. Oh, sorry, not continuous. Okay. All right, so the features that we saw with first order derivatives also hold here. And so the point is that this thing is continuous as a function of all of its arguments, okay? Even though um, if you break this formula down, it's not continuous in any aspect. Okay, so it's kind of a weird thing about this theory, and it has conclusions, sorry, consequences in geometry, as we'll see later. Okay. All right. Let's say some useful things about differentiability of higher order. Okay. So the first thing we'll talk about is the fact that if you compose two mappings of class CK, that it's also of class CK. So this is called so we saw this in the case of k equals 1, and we called that the chain rule. Okay. Um, but here we're going to call this the composite mapping theorem because we're composing mappings. Okay. And so what this says is uh, we have locally convex spaces. So we have two mappings we're going to compose. So there's going to be three locally convex spaces. We're going to take open sets N in U and O in V. Okay. Then I'm going to take mappings. V is going to be CK from N into V. Psi is going to be CK from O into W, right? And I'm going to ask that phi of N is contained in O. Okay. And that just makes sure so if phi of n is contained in O, then because psi maps O into W, then I can compose phi and psi. That's the main point there. Okay, so then the composition is a class CK. Okay. Um, so this will prove, because I think it's a useful uh, um, illustration of how you use our definitions of class CK. And it's not too long and tedious. All right. Okay, so we prove this by induction on K. So the base case, K equals 1, sorry, 1, is the chain rule, which we proved a couple lectures ago. All right, so now suppose that the result is true for K equals M. Okay, and so that means that if I have two mappings of class CM, and I compose them, I get a mapping of class CM. All right, so that's the induction hypothesis. And so I want to show that the same conclusion holds for k equals m plus 1. All right. And so I'm going to assume that phi and psi are of class Cm plus 1. Right, and then I need to prove that their composition is of class Cm plus 1. Okay, so assume that phi and psi Cm plus 1. Okay. All right, so this is just so to prove that their composition is of class Cm plus 1, I have to do two things. All right, so let me maybe say this slowly and clearly, because I think this again is a good illustration of the definitions of what it means to be of class Ck. All right. So to show that um, psi composed with phi is of class Cm plus 1, we have to do two things. We have to show that the composition is of class C1, right? That's what the definition says. The D, I'm sorry, that the composition psi composed with phi is of class C1. And that the derivative of the composition is of class Cm, right? And that's what will allow us to conclude that the compositions of class Cm plus 1. That's the definition. Okay, so that's what we need to do. So certainly, because we're assuming the result is true for k equals m, it immediately implies that the composition has to be of class C1. Okay, so certainly psi phi is of class C1 since it is assumed to be of class C m plus 1. Okay, so that part is easy. All right, so the interesting part is showing that the derivative d of the composition is of class Cm. All right, so what we do is we write down the derivative. Okay. And the derivative is d, I think I'll need more space, d of psi composed with phi, okay, at a point x in the direction u is d psi of phi of x, comma, d phi of x u. Okay, that's the formula that we had last time. Okay. All right. So now what we're going to do is we're going to take a look at this side. Okay, and we're going to rewrite it as compositions of things that we already know are of class CM, and that will give it to us by the induction hypothesis. Okay, so um, certainly I know that d psi is of class CM. Okay, because I'm assuming that phi and psi are of class CM plus one. Right, so this is of class CM. Good. Um, This is of class, oops, easy. So this is of class CM, okay, because it's of class CM plus one, okay, and similarly, this is of class CM plus one. So we just have to kind of organize things in the right way. And in fact, from what I said, I think it certainly becomes immediately believable that this thing will be of class CM. But let's organize that in a good way. So let's write. Notice that phi of x is phi composed with PR1, excuse me, the projection onto the first factor of this thing. Okay. And so again, PR1 is a mapping from N cross U into N. Well, let me make it U, because N is contained in U, so I can make this U. Okay, and it sends X and U to X. Okay, so this formula is certainly true. Okay. Um, and PR1, this mapping, so PR1 is the restriction of a continuous linear mapping to N cross U. Okay. Right, so N sits, so this thing sits in, well, I can write it down. Okay, so this thing sits inside U cross U. Okay, and if I think of PR1 as being a mapping from U cross U into U, it's certainly linear. Okay, and so this thing is just the restriction of a linear mapping to that. Okay, and we know that linear mappings are infinitely differentiable. So thus, PR1 is of class C infinity. All right. Okay, so thus, B composed with PR1 is of class CM F by the induction hypothesis. Okay. Because this is infinitely differentiable. The assumption is that this is of class Cm plus one, therefore it's also of class Cm. Okay, and so the induction hypothesis is that the composition of two mappings of class Cm is a mapping of class Cm. Okay, so it's of class Cm. Okay. By definition, d phi is of class Cm because phi is of class Cm plus one. Okay, all right, so now what we do, okay, is we note that phi of x d phi of x and u, another way to write that is to write it as phi composed with PR1 of x and u. Okay, so let me write it like this. D phi of x and u. Okay, so this is a mapping which takes arguments of x and u, okay, and returns a pair of things. The first one is this component, and the second one is this component. All right. All right. So um, the mapping u maps to the pair. And so this is in n cross u, okay, which maps to this thing. Okay, and where does this thing live? This lives in V, and this lives in V. In fact, this lives in not just V, but it lives in O. O cross V is continuous. And we'll prove this next time. Oh, sorry, it's not just continuous. It's of class CM. Okay. So we last time we proved that mappings into products are C1 if each component is C1. Well, that's also true for CM, and that's all that we're using here. But we'll prove that next time. It's not hard to prove. It goes pretty much like the proof in the C1 case. Okay, so that we're not missing much here, but we'll fill in the gap of that next time. Okay, and then finally. Okay, so basically we're taking this formula for the derivative of the composition, and we're just breaking it down into its little components and writing it in terms of things, each of which we can verify is of class CM. Okay, so we've just verified that this thing as a function of x and u is of class CM, and we certainly know that this is of class CM. Okay, so d psi composed with phi is equal to d psi composed with this thing. Okay, is of class CM by the induction hypothesis. Okay. And so there's a lesson that comes out of this. And the lesson is that you can very often prove useful things just by writing a kind of a formula like this, okay, by writing that as a composition of things, like I've done here. Okay, and then by looking at each of the elements that you're composing, you can maybe prove what you need to prove about that. So it's a useful tool that shows up all over the place in this analysis. Okay. All right, so I'm going to stop there, and I'm sorry I started late. Like I said, there were some problems. And barring that, I'll see you on Monday.